Hello everyone, welcome back. This is lecture 2 and we're going to continue our discussion on differential equations. In this lecture we're going to talk about first order linear differential equation. Well, first, what is a first order linear differential equation? The standard form of such an equation is this. Y prime plus p of x times y equals q of x. Okay, and here p, q are arbitrary functions of x. Okay. So first order means the highest order derivative involved is the first order derivative. So look at this equation here. This is first order derivative. This is y itself, which is 0th order derivative, and this is just a constant term that does not involve y at all. When I say constant, I mean does not involve y. Okay, so this is a first order linear differential equation. If we have, say, y double prime plus y prime equals q of x, then that's a second order differential equation. And linear means that the equation is linear in terms of y, not x. So p and x do not have to be linear equations of x. Linearity here just means the coefficient in front of y prime, y, are functions of x. Okay, are things that do not depend on y. So look at the y prime term here. The coefficient is 1, which is a constant, and the term that involves y has coefficient p of x, which is a function that depends solely on x, and of course a constant term that does not depend on y at all. So that means it's a linear differential equation, linear being in y. Okay, say if we have an equation, say y double prime times y equals some function q of x, this is not linear. Okay, so this is the standard form of a first order linear differential equation. Now let's try to solve it. Remember in the last lecture we talked about separable equations, and what we did with separable equations is we separated the two variables y and x. We grouped all the things that depend on y on one side and all the things that depend on x on the other side, and integrate with respect to x on both sides, right? So here we can, it won't work, but we can try to use the same method and see what happens. So let's try to integrate with respect to x. Then the left-hand side becomes y prime, let me just write dy dx, okay, and that's a function of x, and then plus p of x, oops, times y of x dx equals the integral of q of x dx. Now, if since q and p are both known functions, then the right-hand side can be easily evaluated. And if we look at the left-hand side, this entire thing times dx, okay? If we look at the left-hand side, you realize that the integral of dy dx is just y, right? So this term comes out to be just y. But the issue is, since y is unknown, there's no way to evaluate the integral of p of x times y. It's just, since y is unknown, it's just not something you can compute, right? So we're in trouble. We cannot just directly apply what we learned in the last lecture from the separable equations. So here we need to use a medium called the integrating factor. Okay, let me first write out what the integrating factor is. The integrating, uh, let me just show the entire process of how to derive an integrating factor. So the idea is this. First of all, uh, this doesn't work. The idea of an integrating factor is this. Well, since the problem is p of x times y of x, because this is something that we cannot integrate, what if we multiply the entire equation by something we call an integrating factor, and that thing makes the left-hand side computable? Okay, so we want to look for a function called I of x such that y prime of x plus p of x times y of x, this entire thing times I of x equals the derivative of the product y of x times I of x. Okay? Now, why do we want this? If we can find such an integrating factor, I of x, then you multiply the entire equation by I of x and obtain this equation. So just multiply I of x on both sides of the equation. You get um, y prime of x plus p of x y of x times I of x equals I of x q of x. Right? So this is nothing complicated. We're just multiplying the equation by the same thing on both sides. Now suppose we can find such an I, then the left-hand side immediately becomes d dx of y of x times I of x. Right? Now this is something that's integrable. Why? Because, well, it's the derivative. It's the derivative of y times I with respect to x. So if we integrate this thing with respect to x, the integral and the derivative will cancel out and just give you y of x times I of x. Right? So if we integrate both sides with respect to x, what do we get? We just get y of x times I of x equals the integral of I of x times q of x dx. Now, since we know what I is, then we get our solution. Y of x equals 1 over the integrating factor I of x times the integral I of x q of x dx. Now, depending on what I and q actually are, this integral may or may not be explicitly evaluated, but nonetheless, this is a fixed expression in terms of x, right? So we solved this equation. Okay, so this is why we look for an integrating factor that satisfies this condition. It's precisely because we want to turn the left-hand side into something that can be integrated with respect to x. So the only difficulty now lies in, well, what this integrating factor is. So let's find an integrating factor. I of x. Okay, so remember that the integrating factor is any function that satisfies this. Let me just rewrite this. It's y prime of x plus p of x y of x times I of x equals d dx of y of x I of x. Okay, now let's distribute the multiplication. We get y prime of x times I of x plus p of x I of x y of x equals d dx of this product. By product rule, we have the right-hand side equals y prime of x times I of x plus I of, sorry, yeah, plus I prime of x y of x. Page. Okay. So we just applied the product rule and turned this into this. Now since y prime times I cancels out, so we're just left with p of x times I of x times y of x equals I prime of x times y of x. Divide y of x on both sides, we get p of x times I of x equals I prime of x. Okay, so an integrating factor I is a function such that an integrating factor is a function I such that it satisfies this condition right here. We've simplified the integrating factor condition, right? Now, this is an equation we know how to solve. Why? Because it's a separable equation. If you rewrite I prime into di dx, you'll realize this is di dx, well, 1 over I of x times di dx equals p of x. So all I've done is dividing both sides by I of x and change the notation I prime into di dx. And let's integrate both sides with respect to x. And the left-hand side, by chain rule, is 1 over I of x. Not I of x, I mean 1 over I. So, and then di equals the integral p of x dx. Now the integral of 1 over I is ln of I, right? So we have ln of I equals the integral of p of x dx. Okay, and then exponentiate both sides, we get I of x equals e to the integral of p of x dx. So we've solved this problem. So for any for a general linear first order differential equation, we first find the integrating factor I of x using this formula. Then we plug it into this formula to obtain our result, to obtain our solution y. I forgot to mention this is uh, this is actually not entirely correct. Technically, when you integrate 1 over I, you're supposed to get ln of absolute value of I of x, right? So, and then you do the same thing, exponentiate both sides, then you get absolute value of I of x equals this, and then I of x equals plus minus e to the integral p of x dx. So this is technically the complete answer. But remember that the integrating factor is any function that satisfies this condition. So we just pick positive. You can certainly pick minus e to the integral of p of x dx. You can even pick 2 times this, but why make it so? Why make it more complicated, right? So we usually just pick the simplest one. We pick the positive integrating factor I of x equals e to the p of x dx. Okay, so the first step of solving a first order linear differential equation is compute the integrating factor this, and then use this formula to compute our solution y. Okay, all right, let's look at a couple examples. First, the first problem is y prime plus y equals e of x. Okay. All right. So let's go back to our standard form of the first order linear equation. So y prime plus p times y equals q. So here our p of x is 1. Q of x is e to the x. Now let's use this formula right here to compute the integrating factor. I of x equals e to the integral of 1 dx, which is just x, right? So this is e to the x. Once again, as I said, technically this is an indefinite integral, so you end up with a plus c at the end, and then you get e to the x times e to the c, and since e to the c is arbitrary, you get an arbitrary constant times e to the x. What I'm saying is, if you add like 2 or 3 in front of e to the x, it will still be an integrating factor. But again, we usually just pick the simplest one. We don't add any arbitrary constant at the end, so we just use e to the x. Okay. All right. So this is our integrating factor, and the formula for the solution is this: y of x equals 1 over I of x times the integral of I of x q of x dx. So it's 1 over e to the x, then times e to the x. What is q of x? Q of x is again e to the x dx. Okay, 1 over e to the x is e to the minus x, and e to the x times e to the x is e to the 2x. Okay, and the integral of e to the 2x is, well, it's 1/2 times e to the 2x. This is an indefinite integral, so we have a plus c at the end. Distribute the multiplication, you get 1 over 2 times e to the x plus c times e to the minus x. Alright, so this is the general solution of the first problem. Let's look at another problem. Xy prime minus 2y equals x squared. And here x is positive, so we look for a solution when x is positive only. Okay, this is slightly more complicated than the last problem. First of all, it's not even in the standard form, right? So the first thing we always do is turn the equation into the standard form. How do we do that? So the standard form is an equation where the coefficient in front of y prime is 1. So we just divide everything by x. Divide the entire equation by x. Okay? And we get y prime minus 2 over x times y equals x. So this becomes our standard form. Okay? And once again, let's find out what p and q are. P is the coefficient in front of y. Remember, note that it's not 2 over x, it's minus 2 over x. Okay? And q of x is just x. And the integrating factor using the formula is e to the integral of p of x dx. So we have, this is e to the integral of minus 2 over x dx. Okay, pull the minus 2 out, so you get, this is e to the minus 2 times the integral 1 over x dx. Now since x is positive, given by the problem, the integral of 1 over x is ln of x, right? So this is e to the minus 2 ln of x. And e to the ln of x is x, so we get this is x to the minus 2. If some of you are not sure about this calculation, what I'm doing is this. So this equals e to the ln of x, this entire thing to the minus 2. And e to the ln of x is just x, so we have this is x to the minus 2, or 1 over x squared. Okay, plug this in, we get y. Let me just rewrite this, rewrite the formula for y. Y is 1 over I of x times the integral of I of x times q of x dx. So if I of x is 1 over x squared, then 1 over I is x squared. So x squared times the integral of 1 over x squared times x dx. You get x squared times the integral of 1 over x dx. Once again, since x is positive, this is ln of x plus c. Okay, so this is the general solution of this problem. Now let's look at an example of an initial condition problem. Problem 3. Y prime plus 2y equals e to the minus 2x with the initial condition y of 1 equals 4. So we do the same thing. P of x is 2, q of x is e to the minus 2x, and then we use them to compute the integrating factor I of x, which is e to the integral of p of x dx. So that's e to the integral of 2 dx, which is just e to the 2x. Okay, and then y of x equals 1 over I of x times the integral of I of x q of x dx. 1 over I of x is 1 over e to the 2x, which is e to the minus 2x. Now, I is e to the 2x, q is e to the minus 2x, so the product is just 1. And if you integrate that, you get x plus arbitrary constant c, right? Okay. Yeah, so so this is the general solution. Now we plug in the initial condition to find the particular solution. Y of 1 equals e to the minus 2 times 1 plus c, and this equals 4. Okay, so we get e to the minus 2 plus c times e to the minus 2 equals 4, and therefore c equals, well, 4 minus e to the minus 2 divided by e to the minus 2, so times e to the 2, which just gives you 4 times e to the 2 minus 1. Okay, and put it back in, we get y of x equals x times e to the minus 2x, so I'm distributing the multiplication plus this expression for c. Oops. Times e to the minus 2x. This is an initial value problem. Next, let's look at an application of the first order linear differential equation. So suppose you're setting up a continuous annuity trust fund. Okay, so a continuous annuity what it means is that you're transferring every year $1,000 from your checking account to your trust fund. $1,000 is transferred. And it earns an 8% annual interest, compounded continuously. Compounded continuously just means like you're getting paid interest, and that interest earns you more interest. So it's like a snowball rolling. You get more and more money eventually. Okay, And so the question is, what is the balance after 20 years? The balance in your trust fund, of course, after 20 years. Okay, to solve this, let's first use the variable y, okay, as the balance in the balance of your trust fund. And t is the number of years since you started the trust fund. Then we get the differential equation dy dt equals 1000 plus 8%, which is 0.08, times y. Okay, so this becomes a first order linear differential equation problem. We use the same method to solve it. So first, let's put everything on one side. We get dy dt minus 0.08y equals 1000. Let's write out our P and Q. P of t is minus 0.08 and Q of t is 1000. Then the integrating factor I of t is e to the integral of e to the integral of P of t dt, which is e to the minus 0.08t. Then y of t, by the formula 1 over I times the integral of I of t Q of t is e to the 0.08t times the integral 1000 times e to the minus 0.08t dt. Okay, evaluate this integral. We get minus 1000 divided by 0.08 times e to the minus 0.08t plus c. Right, minus 1000 divided by 0.08 is minus 12,500. So we get minus 12,500 e to the positive 0.08t and e to the minus 0.08t cancels out, becomes 1. So we're just left with this constant plus c times e to the 0.08t. Alright, and this problem has a hidden initial condition, which is since t is the number of years since you started the trust fund, then at year 0, before you put any money in it, the balance should be 0, right? So we have y of 0 equals 0. This is the initial condition. Okay. Then let's plug this condition into our solution. We get y of 0 equals minus 12,500. E to the 0.08 times 0 is e to the 0, which is 1. So it's just this plus c. Okay, and this equals 0, which gives us C equals positive 12,500, and therefore, oops, a new page, and therefore y of t equals, oh, let's distribute the multiplication. Oh, never mind, we already did that. Yeah, let's just plug C in there, and we get our solution. Y equals minus 12,500 plus 12,500 times e to the 0.08 t. All right, let's look at a couple more applications of differential equations. First, a common problem is a common ODE problem. ODE stands for ordinary differential equations. That's what we've been doing. The other type of differential equations is partial differential equations, which involves partial derivatives. So everything we've been doing so far is ordinary differential equations. Another common application is the modeling of chemical reaction. Let me give an example. So suppose during a chemical reaction, substance let me just start a new page. Sorry. Substance A is converted into another substance B at a rate that's proportional to the square of the amount of A. Okay, and then when T is 0, when T equals 0, 60 grams of A is present. And after 1 hour, and here we measure T in unit of hours, so 1 hour means T equals 1. After 1 hour, 10 grams of A is left. Okay, and let's ask how much of A is left after 2 hours. All right, here let's just use the letter A to represent the amount of A left. Okay, And obviously we have two initial conditions, or two values to use. The first one is a of 0 equals 60, and then a of 1 equals 10. And we use the first condition to derive a differential equation. All right. Hey, sorry. That's too many A's. Let's just follow the textbook, and we're going to use y to represent the amount of A left, of substance A left. Okay, then the problem can be written as dy dt is, well, it says dy dt is proportional to the square of the amount of A. So dy dt is proportional to y squared, and proportional can be written as a constant k times y squared, where this constant k is unknown at the moment. Okay, and then the two initial conditions, y of 0 equals 60, and y of 1 equals, 10. All right, let's solve this. dy dt equals k times y squared. Now this is a separable equation, so we don't need to do the integrating factor and all that. We just do it the old-fashioned way. dy dt, 1 over y squared times dy dt equals k. So we integrate both sides with respect to t. And the left-hand side is 1 over y squared dy equals the integral of k dt. And then we're left with 1 over y squared gives us minus 1 over y, right? Yep. And the integral of k is kt plus arbitrary constant c. Therefore, y is minus 1 over kt plus c. Now we have two unknown constants, k and c. That's why we need two initial conditions. So let's plug these in to solve for k and c. Y of 0, plug 0 into t, we get minus 1 over c equals 60. That immediately tells us c is minus 1 over 60. Okay, and then y of 1 is minus 1 over k. Now we know what c is, so we can plug it in, right? So this is minus 1 over k minus 1 over 60, and this is 10. Okay, all right, so we just need to calculate k. If minus 1 over this is 10, then divide both, or divide 1 by both sides, we get minus k minus 1 over 60 equals 1 over 10. Right, so k minus 1 over 60 equals minus 1 over 10. Therefore, k equals minus 1 over 10, then plus 1 over 60. And this will be minus 5 over 60. Then we have our answer, where you just plug k and c in there, and we get our answer. Okay, let's look at another real-world problem here. So problem 3. Suppose we have a tank, a water tank, contains 250 liters of a salt solution that which has a concentration of 0.45 kilograms per liter. Pure water is added in the tank at a rate of 40 liters per minute, and the solution is drained at the same rate. Let's just write again, at the rate of 40 liters per minute. Okay, to solve this problem, first let's write S as the amount of salt. Notice that it's the amount of salt in a water tank. It's not the concentration of the salt solution. Okay, so it's the amount of salt in the tank. And T obviously is time, and in this case it is measured in minutes. Okay, now if S is the amount of salt in the tank, then we know, so first of all, since water is added at 40 liters per minute, and then the solution is drained at the same rate, that means the amount of solution in the tank remains the same for all time. So there's always 250 liters of salt solution, no matter the concentration. There's always 250 liters of stuff in the tank, right? Since the volume of the solution is a constant, then if S is the amount of salt, then S divided by 250 is the concentration. Of the salt solution, right? Okay, then we can derive the differential equation, which is ds dt. Ds dt physically represents the rate at which the amount of salt in the tank is changing. Now, we're adding 40 liters per minute, but it's pure water we are adding in, so that means there's no salt being added into the tank. Okay? So we are the amount of salt in the tank will decrease continuously because there's no salt being added to the tank, and the solution drained contains salt. So that means the salt is continuously uh, the amount of salt is monotonely decreasing. Okay, the liquid is drained at the rate of 40 liters per minute, and we have the concentration of the liquid, which is S over 250. So the amount of salt leaving the tank is S over 250 times 40. There's a minus sign because it's the salt leaving the tank. Okay, and 40 divided by 250 is 0.16, so this is minus 0.16 S. This is once again a separable equation. All we have to do is divide both sides by s. We have 1 over s ds dt equals minus 0.16. Again, integrate both sides with respect to t. We have the left-hand side becomes the integral of 1 over s ds. The right-hand side is the same. The integral of 1 over s is ln of absolute value of x. Now, since s is the amount of salt, so physically it can't be negative. Since it's positive, we can get rid of the absolute value sign and just left with ln of s. And the right-hand side is minus 0.16 t plus arbitrary constant c. Then exponentiate both sides, we get s equals e to the minus 0.16 t times e to the c. Okay, let's just do step by step. Plus c. Now e to the a plus b equals e to the a times e to the b. Therefore, this is e to the c times e to the minus 0.16 t. Let's call e to the c c tilde. Okay, so c tilde equals e to the c. All right. Then we notice the first sentence of the problem gives us an initial condition. It says the tank contains 250 liters of salt solution with a concentration of 0.45 kilograms per liter. That means at time 0, the tank contains 250 times 0.45 kilograms of salt. So we have S of 0 equals 250 times 0.45. And this is 112.5. So we have C tilde times e to the 0, which is just 1, equals 112.5. And we now have, as of t equals 112.5 times e to the minus 0.16 t. All right. There's a second part to this problem. After we obtain this, after we obtain the amount of salt in the tank as a function of t, we ask what time is there 39.5 kilograms of salt remaining in the tank. This is pretty straightforward, so we're saying S equals 39.5 and compute T. Okay, so 112.5 times e to the minus 0.16 t equals 39.5. And divide both sides by 112.5, we get e to the minus 0.16 t equals 39.5 divided by 112.5. You should simplify this. Yeah, just multiply, just get rid of the decimal and then divide everything by 5, you may be able to further simplify this. I'm just going to skip that here. Okay, then minus 0.16t equals ln of 39.5 divided by 112.5. T equals this whole thing divided by minus 0.16. Okay, if this shows up on the web work, you can either leave it like that or type it into a calculator and compute the decimal value. Although sometimes web work does not accept decimal value, it really forces you to type in the exact solution. So if that's the case, then this is the answer you want to use. All right, that's it for today. The web work assignments have already been posted, and I finally got access to Canvas. You should be able to see the syllabus. You should be able to see the syllabus there. There will be weekly quizzes. I will send the Gradescope page either tomorrow or the day after tomorrow. All the quizzes are going to be released on Monday, starting the second week. For the first, what else? Yeah, for the first 2 to 3, I think it's the first 3 web work assignments. You will get a couple extra days because of the delay of the Canvas and web work setup and all that. All right, starting next week, we'll move on to Chapter 7 of the textbook, which is, I believe Chapter 7 starts with 3-dimensional coordinates, and we'll go on from there.